Welcome to Chapter 2 of our journey into Noble Journey. In this lesson, we will explore fascinating ideas from projective geometry, starting with the concept of projective space. Along the way, we'll make sense of two powerful ideas: the perspectivity and projectivity, which helps us understand how geometry works in photography, architecture, and even 3D graphics. Let's begin with the concept of space in geometry. When we define a space using certain rules or properties, called axioms, we're creating a structure. An axiom is a basic rule or assumption that we accept as true without needing to prove it. These rules are the foundation on which we build the set or the rest of our geometry. Examples of which are: through any 2 points, there is exactly one straight line, or a line must have at least 2 points, or two different lines intersect at most at one point. If all those rules can be followed without contradiction, we say the system is consistent. If not, it's inconsistent. So to trust a geometric system, it must first be consistent. Or we could construct a possible structure that satisfies all the axioms or all the conditions. So here's a little structure to think about. Suppose we have 7 points and 7 lines, where each line contains 3 points and each point lies on 3 lines. This kind of system is simple, yet rich in structure. It helps us explore foundational geometric ideas without overwhelming complexity. Is this system consistent? Let's see in the next slide. So in the previous slides, we have the following conditions. We have, there are 7 points in 7 lines. Each line has 3 points and each point is on 3 lines. If we label the points 0, 1, 2, 3, 4, 5, and 6, we have 7 points. And if we choose the lines connecting 3 of these points, then we could satisfy both the conditions we set in condition number 1. But each line has 3 points and each point is on 3 lines. So if we try to draw 3 points here and we try to connect them with a line, and then we have another 2 points here and connect them with a line and another point here, we already have 1, 2, 3, 4, 5, 6 points. And we are required to have 7 points. So if we try to draw here the 7th point and connect them, or connect the 3 points with a line, and here is another line, we could have the 6 lines. But where is the 7th line? So here is the 7th line. So we have completed the conditions. So this system is consistent because we have figured out the conditions into our structure. Now let's define the dependent system of axiom. An axiomatic system is called dependent if we can prove one axiom using the others. But if every axiom stands on its own, meaning we can't deduce any one from the others, then it is called an independent axiom. A good axiom is both consistent and independent. So here, we consider the system with the following properties: that there are 6 points and 4 lines, and each line has 2 points. Each point is on at most 4 lines. Is the system consistent? Yes, because we could construct a figure or figures based on the given properties, just like the ones shown on the slide. But is it dependent or independent? We claim that this system is independent. In fact, it is easy to see that axiom 3 immediately follows from axiom 1. That is, if there are only 4 lines, then clearly no point can be on more than 4 lines. So if you could notice in the figures, we could see that no point can be on more than 4 lines because there are just only 4 lines and there are 6 points. So it's impossible to cover all the 6 points with just 4 lines. Now let's have the near linear space. A near linear space is a space S of PL wherein P stands for the points and L stands for the lines, such that any line has at least 2 points and any 2 points are on at most 1 line. Let's have this as an example. Let P be the points or the set of points 1, 2, 3, 4, 5, 6, and L be the set of lines that connect the points 6 to 4. This pertains to one particular line. Another line is the line connecting 2, 3. And another line is the line that connects points 3, 4, 5. And another line that connects points 6, 3 as shown in the figure. Notice that the point 1 is not connected by neither of the 4 lines. This is a near linear space because any line has at least 2 points. Any line has at least 2 points. So in the list of lines, there are at least 2 points. So the first line contains 3 points, so it satisfies the at least 2 points na condition, and 2 points are on at most 1 line. So there must be one line or no line that connects each 2 points. So that's why it explains that point 1 is neither connected by a line. So this is a near linear space. Okay, here is another example. Let P be the set of points 1, 2, 3, and L be the set of lines, which includes the empty set, the line connecting points 1, 2, and the line connecting points 1, 2, 3. A figure corresponding to this space is drawn below. So there must be a line that contains 1, 2, and 1, 2, 3. So 1, 2 is connected by the curved line, and the 1, 2, 3 are connected by the straight line. Note that it is difficult to draw the empty set because it's empty. It must not appear. Clearly, this is not a near linear space because it violates both NL1 and NO2. Now, we have here the restriction of S to P prime. So let S be the set of points and lines to be a linear space. A near linear space. A near linear space R is equal to P prime L prime to be called a restriction of S to P prime if P prime is an arbitrary subset of P and L prime is the set of intersections L intersection P prime to any L in L with at least 2 points in P. So what does this mean? What happens if we look at some of the points in the space? The idea of restriction allows us to take a subset of the points and see what geometry remains. If we pick a new set of points P prime, then the lines in our restricted space are just the parts of the original lines that pass through at least 2 of the points in P prime. Okay, let's have an example. Let P be the set of points 1, 2, 3, 4, 5, 6, and L be the lines connecting points 1, 4, 1, 2, 2, 3, 1, 3, 5, respectively. If P prime is the set of points 2, 3, 4, then the restriction of the space PL to P prime is R is equal to P prime L prime, where L prime is the set of points or the set of line that connects only 2, 3. To make it simpler, imagine you're playing with a set of points and lines. The points are just labeled as points 1, 2, 3, 4, 5, and 6, And the lines are just group of points that are connected. For example, in this case, 1, 4 means there's a line going through points 1 and 4. 1, 3, 5 is a line that passes through 1, 3, 5, and so on. Now, if you say, I only want to look at a smaller part of this space, or just the points 2, 3, 4, which pertains to your P prime, you're doing what's called a restriction. You're zooming in and focusing on a smaller set of points and asking which lines still exist if I only care about the points 2, 3, 4. So how to find the restriction? So first we look at the original lines on ask. Does this line include only points from our smaller set 2, 3, 4? And does it include at least 2 points from that set? Because a line must have at least 2 points based on the near linear space definition. Now let's check the lines one by one. For the line containing 1, 4, it includes 4, the point 4, but point 1 is not in P prime because P prime contains only the points 2, 3, and 4. So we excluded this line. For the second line, I'm connecting points 1, 2. This includes point 2, but point 1 is also not in P prime, so we also excluded this line. Another is that we have the line connecting 2, 3. So both points are in P prime, so we keep this one. And the last line is the line that connects points 1, 3, and 5, but only point 3 is in P prime, so we also exclude this one. So the only valid one, or the only valid line that is left, is the line that connects 2, 3. Hence, this is our restriction. Okay, let's have another example. Consider the system with P is equal to 1, 2, 3, 4, 5, and each point is a line as represented below. So we let P prime to be our points 1, 2, and 3. So here we are told that P prime is 1, 2, 3. So this means we're going to zoom in and only focus on points 1, 2, and 3. And we want to find out which lines still exist among just 3 points. So we look at the diagram and do some checking. First, do points 1 and 2 have a line? Yes. Another, do points 2 and 3 have a line? Of course. They are connected by a line. And do points 1 and 3 have a line? So yes, they are connected by a line. So the restriction of the given space to P prime, where L prime is equal to the lines that connect the points 1, 2, the points 2, 3, and the points 1, 3, which is represented in the figure below. The restriction of the system gives us the points 1, 2, 3, where all the segments connecting them forms a triangle. So now you're working with a smaller structure made up of only the selected points and the lines that still make sense with those points. So here is a simple analogy of restriction to real life. Imagine you're using a big map of 5 cities, which may be represented by points, and every city is connected to every other. But now you're only interested in cities 1, 2, and 3. Hence, you want to fold the rest of the map and only keep the roads that connect those 3 cities. So this is exactly what we call a restriction in geometry. Okay, now let's define a linear space. A linear space is a space P of L of points and lines such that any line has at least 2 points and 2 points are on precisely one line. To smoothen out some confusions, both near linear and linear spaces are ways to describe systems made up of points and lines, just like the connect the dots game. The rules about how points connect to the lines are what makes the difference. For example, sa near linear space, this is somewhat structured but still flexible. It follows 2 basic rules. Every line has at least 2 points, or in other words, no floating lines that connect to nothing. And then any 2 points are on at most one line. So you cannot connect the same 2 points with two different lines. But not every pair of points has to be connected. So it's okay if 2 points are not connected by any line at all. But in the in the linear space, click and fully connected. It also follows the same first rule that every line has at least 2 points, but the second rule is stronger, that every pair of points is connected by exactly one line. That means you must be able to draw a line between 2 points and no skipping allowed. Unlike in the nonlinear space that any point can be not connected. To smoothen out some analogy in real life, for the near linear space, it can be represented by this situation. For example, imagine a group of friends at a party. Some of them talk to each other, so this means they are connected, and some don't. So there's no rule that says everyone must talk to everyone else. So it's okay in the near linear space. But for a linear space, imagine a classroom icebreaker where the teacher says everyone must introduce themselves to everyone else, no exception. So in this case, every person must connect to every other person with one and only one handshake. So the person represents the point and the handshake represents the line because the handshake from one person to another can be called connected. Okay, here's an example of a linear space. Let R2 be the Euclidean plane. A point of R2 is an ordered pair xy of real numbers. A line is the set of points xy satisfying an equation y is equal to ax plus b or x is equal to c, where a, b, and c are fixed real numbers. So this is a linear space. So let me explain. R2 is just a fancy way of saying the 2D coordinate plane. Any point in R2 is written as an ordered pair xy. For example, we could identify in the Euclidean plane or in the coordinate plane the points 2, 3, point 0, -1, or 5, 7. It's the same grid that we use in algebra or in graphing where the x-axis goes left to right and the y-axis goes up and down. Is this a linear space? Yes, it is a linear space because every point can be described using xy and every line is well defined by equations like y equals ax plus b or x is equal to c. And importantly, any 2 points lie on exactly one line, which matches the rule of a linear space. Now let's have this projective plane. Projective plane is a linear space in which any two lines meet and there exists a set of 4 points, no 3 of which are collinear. So a projective plane is a special kind of geometric space where the usual rules of flat geometry are slightly bent to give us new useful properties. It's built on a linear space but adds two special rules. First is that any two lines meet. This means that no matter what two lines we draw, they will always cross at some point. Example in real life is imagine you're standing on a long straight road. The sides of the road look parallel, right? But if you look far into the distance, they seem to meet at the horizon. That's the idea behind this rule. Even parallel lines will meet, just not where you can see it. We imagine they meet at a special point at infinity. So this point at infinity will be discussed in the later parts of our course. Now, this is one big difference from the regular geometry where parallel lines never meet. Based on Euclid. The second idea is that 4 points, no 3 in a line. So there must be at least 4 points and no 3 of them lie on the same line. So in real life, think of placing 4 pins on a board in such a way that no 3 are lined up straight. That means you can't draw a single straight line through any 3 of them. This ensures the space isn't too flat or simple, and it has enough complexity to be interesting. So what's the big picture? A projective plane is a world where all lines eventually cross, even if it's at infinity. And you can always find a group of points that aren't just lined up. This kind of geometry is useful in the art for perspective drawing, in photography for camera projections, computer graphics where we use 3D modeling, and mathematics where we explore abstract spaces. So to wrap up, projective geometry isn't just about abstract math, it's about how we see, draw, and model the world around us. So by understanding projective spaces and the ideas of perspectivity and projectivity, we are gaining tools that we use in fields from design to physics to computer graphics. And in our next lessons, we will dive deeper into constructions and properties of the projective plane. See you then. Thank you.